In this video, we put all of our knowledge about electric flux to work to develop one of the four fundamental equations of Maxwell's electromagnetic field theory. This is known as Gauss's Law. It's an incredibly powerful law, and it can be used to find electric fields for us, provided the system has symmetry. The system has symmetry, so we know the shape of the field lines, and we know surfaces on which the electric field is constant. Then we can use this knowledge along with Gauss's law to be able to find the electric field. Remember, if we find the electric field, we can multiply by the charge on an object to find the force on that object. But we have to be able to find the electric field. This is one of the ways that we can do it. It doesn't work for a lot of problems, but when it works with tremendous ease, and it gives us great insight. So it is one of the things we really want to be able to do. So Gauss's law for electric field says this. The electric flux, which is proportional to the number of field lines, through a closed surface depends only on the net charge enclosed by that surface. So what I'm saying is that if you take a bunch of field lines wherever they're going in space, and if you were to draw some shape, and it could be the most unusual shape you ever saw, now that shape is a surface. It's enclosing something like a balloon. It's a weird looking thing. It's not two-dimensional, it's three-dimensional. The flux for those green lines going out would depend only on the amount of charge inside and not on the shape. So if you drew different shapes like this blue shape and that purple shape, they have the same flux through them. They don't have the same electric field at different points. They don't have the same area, but they have the same flux. This is the essence of Gauss's law. So, the electric flux, but not just for any surface, for a closed surface, very important, is equal to the enclosed charge. That is, just figure out how much charge is inside the surface and then divide by the permittivity constant. Now, I told you before that I don't tend to remember this permittivity constant. You could find it in UIL tests and such. But if I multiply by 4 pi on the bottom and top, I could get my old friend K. So I prefer this version. 4 pi times K times Q enclosed. And remember, K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. So you usually see it this way in the books, but because I don't remember epsilon naught, I multiply top and bottom by 4 pi. 1 over 4 pi epsilon naught is K, so I get 4 pi Q enclosed. Now, note, and this is important, Gauss's law is only valid for closed surfaces. If the surface is not closed, you can't say anything about the flux in terms of enclosed charge. So it's more limited in scope than the definition of electric flux. But one of the nice things is that if I need to sum up the total flux, I can just find the enclosed charge and divide by epsilon naught, and I don't have to do that little summing thing that we did with that cube a minute ago. So if I look at that, that actually tells me something about that cube. What does that say about that cube? Well, if you remember for our cube example in the previous video, the enclosed electric field, or I should say the closed flux, not the electric field, the flux through the closed surface was 0. This implies that the enclosed charge was 0. Now, that doesn't mean there's not charge in there, but it means whatever plus or minus charges in there are balanced. The net charge is 0. So when I had that cube, and we had these electric field lines going in here and coming out the other side, like that, the fact that all the lines coming in also left tells us there's no net charge inside of there. Now, there could be a positive charge or a minus charge. These guys might have all come into this negative charge, and there might have been a positive charge over here, and there might have been some lines going like that as well. But the net effect is, we don't know what went in here as far as those lines. We never saw those lines. But every line that came in left, that meant the net charge, the pluses and minuses in here, canceled out. Now, we could shrink that cube to the point. And if we do that, we could talk about the charge at each point related to the lines there. So, Gauss's law is very powerful. It tells us something about what goes on inside the box. So, useful facts that you should get out of Gauss's law. The electric flux through a closed surface depends only on the net charge enclosed, not the shape of the surface. So they'll give you different surfaces. Don't get messed up. Like I said, it doesn't matter about my blue box or my green box. Whatever the shape here, doesn't matter about the shape. It only matters about the charge inside to get the flux. Gauss's law for electric fields tells us the cause of flow, which we told you earlier. The cause of flow, because that's what Gauss's law, the flux, tells us is flow, tells us that that is caused by charge, the enclosed charge. Now, the other thing that can be really useful is that we might be able to use this to find the electric field. How? Well, remember our closed flux, we could write that from 1 to n as our electric field on each surface dotted with the area vector on that surface. And if we write that out a little bit, we're talking about the magnitude of the electric field, the area of the surface, and the cosine of some angle. Just like we did with the cube. These are the various fluxes of each one. Now, problem is we'd like to find E. And that's going to be difficult because the E's inside the sum. The only way we're going to be able to work this problem, I don't want to find this. I have a way to find this now. That's Q enclosed. So I have a way to find that side. I want to use it to find this. I need to be able to get that E outside this sum. So one thing I need is that the electric force's magnitude needs to be constant everywhere. So I need to find places where the magnitude of the electric field is constant. I've also got this cosine, and that's going to be a problem. I need that cosine to be 1, -1, or 0. If it's 1, then I can pull that out. If it's -1, I can pull it. If it's 0, it falls out. All I'm going to end up then having is the sum of A. Well, that's just the area of the surface. So I know the surface area of some shapes, like spheres are 4 pi r squared. Cylinders are 2 pi rl, if you're just looking at the side, not counting the ends. So I might be able to work problems with the area if I can get this electric field outside, provided the shape has something special. If you can't find such a shape, then probably all likely, unless they're asking you to do some flux problem, you just don't use Gauss's law. Alright? So Gauss's law is usually used to find an electric field for a special surface called a Gaussian surface, which has these particular attributes. Cosine is 1 or -1 or 0, and the electric field's magnitude is a constant. If you can't figure that out, you don't know the shape of the field, then just don't use Gauss's law. Consequently, Gauss's law is really about symmetry problems, and it doesn't tell you anything about the direction of the electric field. You have to know that, like if you have a charge, you know the field lines go like this. Then if you can tell me the magnitude, I can tell you, like if you could tell me what the electric field is right there in magnitude, I could tell you the direction it points that way. You're going to get the direction from the symmetry. Now I realize this is a lot of information to take. You're going to have to watch it over again, think about it, but mostly you're going to have to work problems. By working problems, you'll begin to see how we do this. Alright, so Gauss law, very powerful law, but it doesn't work for most problems, only for problems that are symmetry. So we're going to work problems involving plates, problems involving cylinders, and problems involving spheres. Those are the three types of problems we'll work. Before we finish this, I want to at least do a couple of problems with flux. Find the electric flux through the blue surface shown below. So here we go, a surface, this weird looking shape. To find that flux, 4 pi K Q enclosed. That's 4 pi times 9 times 10 to the 9th Newton meter squared per Coulomb squared times minus 3 minus 5 is minus 8 plus 2 is minus 6 coulombs. The electric field for that, need to punch a calculator, of course. So we take our calculator and we punch it, and we get minus 6.79 times 10 to the 11 Newton meter squared per Coulomb. Notice how I never did anything with the shape. And in fact, had the shape been like this, I would have got the same answer. And I would get the same answer if the shape was like this, because it has the same enclosed charge. All I need to know is the enclosed charge. Now what if you had a spherical charge right here, 5 microcoulombs, and they give you all this other stuff? I don't care about all that other stuff. It says through the surface area of a sphere. Well, the sphere's around it. It's enclosed. So it's 4 pi K Q enclosed, 4 pi times 9 times 10 to the 9th Newton meter squared per Coulomb squared times 5 by 10 to the minus 6 coulombs. So the electric flux is 5.65 times 10 to the 5th Newton meter squared per Coulomb. I don't care anything about the shape or the radius. I just count the total charge in here. Now if you put some other charge in here, you change Q, you change my flux. That should be flux. Alright, we'll talk to you in another video.